This is section 3.2, part D, standard deviation of residuals. A residual plot, in effect, turns the regression line horizontal. It magnifies the deviations of the points from the line, making it easier to see unusual observations and patterns. If the regression line captures the overall pattern of the data, there should be no pattern to the residual plot. So if this is our original data set on the left, and if this is our residual, on the left, then the original data points are on the right with the X and the Y. You can see that there is a clear pattern to this residual plot, okay? The fact that we have a pattern means that this is not a good fit for the data. So as you can see, a straight line does not appear that is an appropriate model for this data. Here are two important things to look for when you examine a residual plot. The residual plot should show no obvious patterns. A curved pattern is a residual plot shows that the relationship is not linear. The residuals should be relatively small in size, and a regression line that fits data well should come close to most of the points. This means that the residuals should be pretty small. So, standard deviation of the residuals. We have already seen that the average predicted error, or the mean of your residuals, is 0 whenever we use a least squares regression line. That is because all the positive and negative residuals are going to balance each other out. But that does not tell us how far off the predictions are on average. Instead, we use the standard deviation of the residuals, or the S value. To find the standard deviation of the residuals, you're going to take the square root of the sum of all the residuals squared, and you're going to divide this by n minus 2. This gives the approximate size of a typical or average predicted error, or it tells us on average how big your error is, which means the residual. So find the standard deviation of the residuals. What is the standard deviation of the residuals for the NEA change and fat gain problem? Explain its meaning and context. So if you remember, in that last section in the Check Your Understanding, we made this nice table that had all the NEA change, all the fat gain from the observed. We predicted using our least squares regression line, and then we found our residuals by taking the observed fat gain and subtracting our predicted fat gain. Now, if we take all of those residuals again that we already found, to find the standard deviation, we are now going to take those residuals and we are going to square them. Once you square all of those residuals, we are going to add them together or find their sum. We're going to divide that by n minus 2, which since there was 16 observations, this would be 14, and then you will take the square root. And this is going to give us an S value of 0.736 kilograms. So researchers would need to decide whether they would feel comfortable using the regression line to make predictions that are on average off by 0.739 kilograms. Now, you can make residual plots and you can find your S value on your calculator, so you don't have to do all of that by hand. To do that, the first thing you would do is input the data points to make a scatter plot and plot the residuals, or to plot the scatter plot itself. You're going to calculate the equation for the least squares regression line, and you're going to graph the line on your plot. In this case, we know that our equation should be 3.505 minus 0.00344 times x. Now we need to define a new variable. So you're going to go back to your list and you're going to go over to list 3. And we want list 3 to be our predicted values from our regression line. So you're going to go up, you're going to highlight list 3, and you're going to enter the command of what your equation is. So 3.505 minus 0.00344 times list 1. And to get list 1, you can hit second and then the number 1, and it'll get you list 1. And you can press enter. It should then fill in all of list 3 with your predicted fat gain values. Now we're going to go over and we're going to define list 4 to be our residuals. Now we know our residual is the observed minus the predicted. All of our observed fat gains are in list 2. All of our predicted fat gains are in list 3. So if you highlight list 4, you're going to enter the command of list 2. To get that, you would hit second 2 minus list 3, second number 3. Press enter, and this will find you all of your residuals. Now you need to go back to your plots and turn plot 1 off. You don't change what plot 1 is, you just turn it off itself. And you're going to turn off the regression equation. So you're going to go into your y equals and turn that first equation off. We're going to go back to our plots, and we're going to specify that plot 2 will have L1 as the x values and L4, which is the residuals, as your y variable. Once you do this, you can use zoom stat to see our residual plot. So it's going to graph it for you. Finally, we want to compute the standard deviation S. So you're going to calculate one variable statistics of the residual list, which is list 4. So when you do the one variable calculations or one variable stat calculations, you're going to have to change it. Instead of looking at list 1, you want to do one variable stats for list 4. To do that, you would hit second 4 to bring up list 4. The mean of the residuals is 0. Now you could have a little round off error, but it should be very, very close to 0. The sum of the squared residuals, which is the sum of the x squares, is the sum of your residuals squared. So you are going to use the sum of the x squares in this part of your equation to calculate S. So you can say S is equal to the square root of whatever the sum of x squared is divided by n minus 2. How well the line fits the data. So we're going to start looking at the r squared value. A residual plot is a graphical tool for evaluating how well a regression line fits the data. The standard deviation of the residuals, or the S value, gives us a numerical estimate of the average size of our predicted error. There is another numerical quantity that tells us how well the least squares line predicts values of the response variable y, and it's the r squared, or the coefficient of determination. You may have noticed this value when you've done calculations for your regression in the past. You have an r, and right below it on your screen you do see r squared. Although it's true that r squared is equal to just your r value squared, there is a lot more to the story about r squared itself. Suppose a new student is assigned at the last minute to our group of 8 hikers. What would we predict for his pack weight? If we don't know the student's body weight, then we can't use the regression line to make a prediction. So what should we do? So we have our body weight versus pack weight. We have this graph here. So suppose a new student is assigned. What we're going to do is, on the scatter plot of the hiker data that we have studied throughout the chapter so far, the least squares line is drawn on the plot. This means the mean y value, or y bar, is 28.625 pounds, and it's drawn with that blue horizontal line on the graph. So if we don't know this new student's body weight, then we can't know what to predict using the line. Our best strategy is to use the mean pack weight of the other 8 hikers as our prediction. So if we use the mean pack weight, we would get 28.625 pounds. So since we know nothing about this student, we're just going to have to assume that they're average among the group, and we'll just use the average pack weight based on the prediction line. So we have a graph that showed the prediction error if we use the average pack weight, y bar, as a prediction for the original group of 8 hikers. We can see that the sum of the squares for the line SST is equal to the sum of y sub I minus y bar. So that means you're taking all your y values, you're subtracting your y bar values, you're squaring them, and that's going to give you a sum of 83.87. SST means the total variation in the y variable. So it's telling us how much total those pack weights are varying. If we learn of our new hiker's body weight, then we could use the least squares line to predict his pack weight. How much better does the regression line do at predicting pack weight than simply using the average pack weight? So we want to see how much better it would do if we actually use the line instead of just using the average pack weight itself. So if we look at this, our least squares line is the sum of our residuals squared, and in this case, it's 30.9. We will call this SSE, or the sum of the squared errors. So SSE is the sum of the square errors. The ratio of the sum of the square errors over the total variation in the y values tells us what proportion of the total variation in y still remains after using our regression line to predict the variable. In our case, if we do SSE over SST, we're going to get 0.368. So that means that 36.8% of the variation in pack weight is unaccounted for by the least squares regression line. So it's still due to some other type of variation. Let's take this one step further. The proportion of total variation in y that is unaccounted for by the regression line is 1 minus your SSE, or the sum of the squared errors, divided by the SST, which is the total variation in the y values, or 1 minus 0.368, which is going to give us 63.2%. So we interpret this by saying 63.2% of the variation in pack weight is accounted for by the linear model relating the pack weight to the body weight, but about 37% is still not related. So for this reason, we define R squared as 1 minus SSE over SST. The coefficient of determination, or the R squared, is the fraction of the variation in the variable of y that is accounted for by the least squares regression line of y on x. We can calculate the R squared using the formula. R squared is equal to 1 minus SSE over SST, where we know that SSE is the sum of the residuals squared, and we know that SST is equal to the sum of your y values minus the y bar values, which is the mean, squared. If all points fall directly on the least squares line, your SSE, or your sum of the standard error, should be 0, and the R squared should be 1. So if all points are directly on the line, SSE is 0, R squared is 1. Then all the variation in y is accounted for by the linear relationship with x. Since the least squares line yields the smallest possible sum of square predicted errors, SSE will never be more than SST, which is based on what our average was for the y value. In the worst case scenario, the least squares line does no better at predicting y than just using the average does. In this case, the SSE would equal the SST, which means your R squared would be 0. If r squared is equal to 0.632, as it was in that previous hiker example, then about 63% of the variation in y among individual hikers is due to the straight line relationship between y and x. The other 37% is individual variation among the hikers that is not explained by the linear relationship. So what other factors besides body weight might help explain a hiker's pack weight? This could be due to their physical fitness. It could be due to desire to carry the creature comforts, so that makes the hike better for them because they have all this stuff that's going to make them more comfortable. A willingness to share the group's equipment load. So one person may not be willing to help the group carry all the equipment they need to take, so their pack might be lighter. And these are just a few sources of possible variation for the pack weight. It seems pretty remarkable that the coefficient of determination is actually the correlation squared. This fact provides an important connection between correlation and regression. When you report a regression, give r squared as a measure of how successful the regression was in explaining the response. When you use a correlation, the r value, square it to get a better feel for the strength of the linear relationship. So let's check our understanding. Here's the residual plot for the least squared regression of pack weight on body weight for the 8 hikers for the earlier example. So this is the residual. We know the body weight, we have the residuals plotted. The residual plot does not show a random scatter. Describe the pattern that you see. So if we look at this, there is a moderately strong linear relationship. There is one outlier on the bottom. So we do have a line that's going up through here, and we do have one outlier here on the bottom. For this regression, we know the S value is 2.27. Interpret this value in context. Remember that S value is the average error of your residuals, and it predicts that the backpack weight is 2.27 pounds using the least squares regression. So the average error, we're off when we're predicting these backpacks by 2.27 pounds when we make these predictions on average. For the least squares regression of fat gain on NEA, our R squared value was 0.606. Which of the following gives a correct interpretation of the value? Remember, the R squared value tells you how much of your variation is accounted for by the least squares regression line. So since our R squared value is 6.06, we know that 6.06% of the variation in fat gain is accounted for by the least squares regression line. A recent study discovered that the correlation between the age at which an infant first speaks and the child's score on an IQ test given upon entering elementary school is negative 0.68. A scatter plot of the data shows a linear form. Which of the following statements about this finding is correct? So if we know that we have a value of negative 0.68, we know that this is moderately strong. It's not real strong, it's moderate. We do know that it is a negative relationship because this has a negative value. So there is a moderately strong negative linear relationship between the age at first spoken words and later IQ test scores for the individual in this study.